Good morning, everyone. I'm Face of Sarcasm, and I'm doing my episode of End of Mission, the podcast with slides in which we talk about missions that have ended. Oh yeah, sorry. Let me take the duct tape off. Who are you?
You took off the wrong duct tape. That was one of my head. You took my hair. You monster.
Oh, I'm sorry about that.
I'm Paul, the pressure-fed astronaut. You know me as the guy who says things about Starship you don't like to hear.
Yeah. Can't wait to do an episode on that.
Yeah, that's our next end of mission.
Yeah.
Good pictures. If you haven't seen the IFT3 photos, you should definitely take a look at those. They're really stunning.
Yeah. I haven't. I also have to look at those.
Yeah.
But welcome to today's episode of Mars Global Surveyor.
Oh, so isn't this what George Washington did before he became president?
What?
He was a surveyor.
He was?
Yeah, he was a land surveyor, I think.
Oh, I thought he was. Okay, well, never mind.
Well, you learn something new every day. It might be wrong, but you learned it.
I enjoy learning incorrect facts.
Yeah, who doesn't love that? Is this so? We have a few custodial things to cover, and in memoriam. Astronaut Richard Dick Truly died, I think, last week or the week before, end of February. When we get to one of his missions, which are early, like STS-2, I think STS-5, we'll talk about him. But yep, so in memoriam, we lost a shuttle astronaut. The Chandra X-ray Space Telescope is probably going to be shut down this year due to budget cuts. So rest in peace, Chandra.
You're going to make a great next episode.
Yeah, that's the next episode. We'll do that. And then the final thing, the big surprise of this episode. So I got you, Face of Sarcasm, some presents.
Oh yeah, and I have them here. So
Yep.
I'm supposed to open the yellow one first, right?
Yes, the yellow package first. Open that one first.
Okay. Give me a second.
Need help?
No, I got it.
I'll drive the 9 hours to go help you while we record this live. You will get to listen to me. You'll listen to all the music I listen to when I'm driving. So to fill dead air, I've been listening to some Ye Banished Privateers. They're a good group out of Sweden, and they do sea shanties. Well, what did you get?
What is this? Oh, what is this?
Yeah, don't look at the receipt if there's anyone in there. Don't look at that.
Oh, yeah. Okay. Oh, what is this? Oh, look at that. This whole thing.
Yeah, it's a button from the launch.
Oh my gosh.
Yeah, so you can't. No one will see it. Take a
Why
picture
is it a
of
little
this.
baggy? What's this white powder?
Look, that mission's launching it, and you're gonna take a trip too, okay, buddy? That's the purest. That's the purest Mars dust you can get, okay?
99.1% purity.
Yes. So that's a button from the launch.
Wow.
So if you attend the launch, you could have picked that up at the press stand, I think.
This is in surprisingly great condition.
Oh yeah, it is.
It's like about 2 inches tall, 1 inch wide.
I'll edit a picture of it in.
Oh, okay, cool.
Yeah.
Like,
Isn't that cool? Yeah, so I troll eBay sometimes looking for space stuff to see if there's anything interesting. And it was either what I got here, or you could buy one of the tires flown on STS-39.
and you decided to go with a button instead of the tire?
That was $13,000. And I have to go pick it up in Virginia.
This is a great button, by the way. This is fantastic.
So open the other one.
Oh, okay, yeah, because there's two.
Yeah, I got that one too, just so we're clear.
Nice.
Oh, not the Mars Global Surveyor, not that one. I got the one you're opening now for
okay.
myself. There's a few of them.
Yeah, I don't want some stupid button, right?
Yeah, I don't want them dumb things. Need help? Let me drive back for 9 hours.
Yeah. Ooh. Oh. There's So much packaging.
Mine didn't come with such nice packaging. What the heck? I guess they knew it was me. Oh, God. Oh, it's him? He said things about Starship I don't like. Give him crap.
Oh, hang on. Jeez, this is going to take forever to open. Sorry, it's you can't see this, but it's like a Rubik's Cube inside of a mousetrap inside
There's some riddles.
Yeah, there's this weird guy with a bunch of needles standing nearby asking me some questions. I don't like.
Yeah, kind of weird.
Oh. Oh.
Come on, you can do it. I believe in you.
Probably have to edit all of this out.
No, I'm not editing it out. I'm lazy.
Oh, gosh.
I try not to do as much editing as I can.
Ah, and it's got a little Mars Observer button.
Yeah, it's Mars. I got one too.
That's awesome.
Yep. So if we ever go to Kennedy Space Center, you'll wear Mars Global Surveyor. I'll wear Mars Observer in case we get lost.
Yeah.
Or
have you seen my brother? He's wearing a Mars Observer pin.
What's wrong with him? You sure you want to find him?
Can you just describe him? Yeah, he's wearing a pin. Okay. He's wearing a button.
Yeah, I also got me a Titan 4 launch button.
Okay. I see.
Yeah, it's Titan 4 K22, which is that one worked. Don't worry. It was some oceanographic satellites for the Navy.
Okay.
Yeah. So but I got you some buttons.
Nice.
So if we ever do like a NASA social, which I think we should apply for one at some point because it'd be fun, we wear these. So
yes.
Yeah. So we look cool, and they go, look at those nerds.
We could get like a lot of these, and then like have them all like decked out, look like the North Korean generals.
Yeah.
You know, they just have endless, like endless medals. It's just endless buttons. So
We
like,
could do that.
then it's like, oh, do you like space? No.
I just like buttons. Yep. So.
But thank you so much. I really like this. This is great.
This is good. It was either this or a $13,000 shuttle tire.
Would have been worth it. Like, come on.
Yeah. I think you could buy like spacesuits too on eBay. I look around sometimes. Okay. I've been tempted. I've been tempted. I actually found a T-shirt for the first launch of Conestoga from 1982.
Oh.
I was this close to actually buying it, but it was $70, and I thought,
that's honestly not terrible.
So if you want to buy a T-shirt for the first private launch of a spacecraft, well, rocket in the United States, it's on eBay. I think, at least 3 weeks ago it was.
Yeah, one of our loyal viewers probably got it.
No, probably not.
Okay.
They're gonna buy some space mission buttons. That's what they should do.
No, they need to save up and invest in a $13,000 wheel.
Yeah, that's our Patreon specifically to buy a shuttle tire.
Yeah. GoFundMe. I want a wheel.
Yeah. You want what?
Oh, it's a special wheel. Yeah.
One more thing. Speaking of going to Kennedy Space Center, if you're going to Kennedy Space Center on April 21st through 24th, you can go have a chat with astronaut John Bartow, who flew on STS-51F. If you do get a chance to do that, ask him about his mission, not if he liked Space Coke or not.
Yeah.
He'd appreciate that. You'd probably be the first person to ever ask him that.
With all these degrees and experience and everything, the Coke tasted not great.
Yeah, we got wet burps.
Ew.
Yeah. Okay, so this is your mission. Let me make sure I clicked on that. Okay. So
Yes.
let's go to the next slide. This is Mars Global Surveyor.
Yep, so we're talking about Mars Global Surveyor finally after like 20 minutes now.
Yep. Hey.
All right. So, Mars.
Barsoom.
What is Mars? Why is Mars? How is Mars? Well, Mars is named after... Well, Mars is a red planet, right? It's named after the Roman god of war because it's red, right? You look up at it in the night sky, and it looks a little red. And they're like, that's blood for the blood god.
Yeah.
Right? It's like, oh, your planet's named after dirt? Well, ours is named after the blood god. And then the moon's we named after his two kids, Fear and Terror. What's your blood type, by the way? Just out of curiosity.
B positive. As an IB positive, you shouldn't be taking my blood.
Oh, okay.
It actually is B positive, I think.
Yeah.
I used to give blood.
Good
Now
job.
I take.
Fun fact. Mars being red and your blood being red is red for the same reason.
Envy?
No, oxidizing iron.
Oh. That makes sense. That's
Yeah.
actually why when we look for life on other planets, we look for free oxygen, because oxygen likes to bond with things. So if it's not, there's something that's doing it.
Something that generating oxygen.
Yeah.
Trying to kill all of their life accidentally with it.
Yeah. So what are these details about Barsoom?
Okay, so Mars is not actually a god, but rather like a really big pile of rocks. And so the planet is, it's about half the size of Earth. It has a surface gravity of roughly 38% of Earth's, but it's kind of similar to Earth in that it has about a 25-degree axial tilt and rotates 24 and a half hours.
Yeah.
So a little longer than an Earth day, but it's about 1.5 times the distance from the sun than the Earth is. And compared to Venus's atmosphere, which is crushing and
Melts you.
and melts you, Mars basically doesn't have an atmosphere. I mean, it does have an atmosphere, but it's like Venus's atmosphere is like 95 times thicker than Earth's, and Earth's atmosphere is like 95 times thicker than Mars's atmosphere.
I see a theme.
Yeah, it's weird. But like Mars also has a lot greater presence in like popular culture and science fiction.
Yeah, I referenced science fiction. Barsoom. That's what they
Yeah.
called it in the John Carter books.
Yeah, most people just know it as Mars, and no one's read the comic books, so we're just gonna call it that.
John Carter was a book written in 1912.
Yeah,
Yeah,
no one's read it.
I have.
And who are you?
I say things you don't like about Starship.
But yeah, so obviously it has a big place in science fiction and popular culture. It's really interesting. Like the reason why scientists are kind of interested in Mars is that within the inner solar system, you basically have 5 objects: Mercury, Venus, Earth, the Moon, and Mars. And the Earth and Venus are very active and alive planets, with one actively trying to kill you, and the other is Venus.
Mm-hmm.
But like Mercury and the Moon are basically just dead, right? There's like nothing going on there whatsoever. Yeah. But Mars, it's kind of in the middle. It's not really as active as Venus or Earth, but it's not dead like Mercury or the Moon. So it's kind of interesting.
Yeah.
And also, Mars is, as of right now, the only planet known to be inhabited entirely by robots. So,
True. Yeah.
cool.
And so this is, I brought this up before we started this. So right about here is a massive volcano. A dead one, but that's a volcano.
There is one there.
Yeah.
Okay.
Yeah. Because these are all volcanoes, right? This is the Tharsis Bulge right here.
Yeah. We're gonna get into that.
Oh, okay. Yeah. Oh, if you want some science fiction about Mars, Kim Stanley Robinson's Mars trilogy is absolutely the best. It's also very boring, but it's the best on Mars, going to Mars and colonizing it. So.
Nice.
Yeah.
All right. Next slide, please.
I should make the little slide noise, those little, view graphs and those. Hey, this looks familiar.
Yeah. So before we could talk about MGS, we first have to talk about Mars Observer.
Yeah,
See,
my button.
Yes, with your button, and now my button too.
Yeah.
So, so there have been a number of missions to Mars up until this point. This point being the 90s. And so there was the Mariner missions, which is where we get Valles Marineris from, Mariner Valley.
Yeah.
They found this giant gash in the planet.
Yeah.
And there's also then the Viking missions in the middle of the 70s, right? But by this point, in the 90s, it's been almost 2 decades. And scientists are still really interested in Mars. I want to go back to Mars and maybe stay there for a little longer than like one-off missions.
Yeah.
So, this is Mars Observer, right? This took like 8 years of development by NASA JPL. And it was there to observe Mars. Basically, put it into a polar orbit around Mars, and it would do a couple of the mission objectives that you could see, right? It would observe Mars, right?
Wow.
It would determine the global elements and mineralogy. Right? It would define the global topography and gravitational field, establish the nature of the Martian magnetic field. Look at the atmosphere as it goes around the planet, right? All this stuff, and it had a bunch of scientific instruments to fulfill that mission.
Yeah.
But spoiler alert, Mars Observer is a future mission that we are going to be talking about.
It exploded.
So to spare you the details, we'll just say it's going to be a future episode.
It's coming up actually pretty quickly.
Okay. But what we'll say is that Mars Observer was supposed to do all of these things, but the mission ended in August 22nd, 1993, with the details to follow. But for our purposes right now, it's a failure. Mars Observer failed, right? The first mission that was going to try and go back to Mars for a long-term presence failed.
Bit of an issue.
Yeah, that is a bit of an issue. Now, of course, because it failed, it was going to be the first mission. It didn't really do much, which, again, we'll talk about later.
It sent back a few pictures of Mars from a distance.
We'll get into later.
Oh, okay, fine. Gosh.
Okay, well...
You want to go to the next slide, then?
No, not yet.
Okay, fine.
Hang on. So because of this, there was immediate worry that, oh crap, they're going to try and... they're worried that Congress is basically going to try and can any future missions to Mars, and we're not going to go back to Mars for a while.
Yeah.
But obviously scientists want to go back.
Also, just as a note, I think Mars Observer was part of the Planetary Observer program, there were plans also for a lunar observer, I think, which was canned.
I think so too.
Yeah, because that's where they were going to try out the ballistic capture trajectories.
Oh, yeah.
Yeah, which was eventually actually flown about 1993.
Yeah.
No.
All right. So, next slide, please.
Slide noise.
Hey. So, this is where Mars Global Surveyor comes in. So, Mars Observer ends its mission in late August of 1993. Mars Global Surveyor is planned out and put into the NASA budget in February of 1994, meaning they only had 6 months to put it together. And Glenn Cunningham wrote in one of the papers that I read that this was the fastest a planetary mission had ever been developed. And in case you're wondering who Glenn Cunningham is, he's the program manager of the Mars Surveyor program.
Okay.
So the guy in charge.
Yeah. He's an intern. He's the janitor.
Yeah.
It's like in Good Will Hunting. He's just Matt Damon writing on the chalkboard. Oh, wow, you got a Mars mission. Wow, that's neat.
Oh, good job, guys.
Wow.
But yeah, so it's basically just Mars Observer, but different.
But works.
But works. But Congress approves the mission in October of 1994 with a launch in November 1996, because that's when the next launch window is. So they basically have 2 years and only $154 million to do it because of the faster, better, cheaper, best 2 out of 3 concept.
Yeah, we've seen a few of those.
Yeah. So part of the cost-saving measure that they're going to implement is not bringing as much fuel on board. So the way that...
Because Mars Observer exploded.
Yeah, Mars Observer exploded. So part of the mission then is aerobraking, right? This was recently demonstrated, relative to MGS, recently demonstrated with one of the Magellan missions at Venus.
Oh, the Magellan mission.
Okay, the Magellan mission at Venus.
Yeah, and Highton did it first.
Okay.
Like a week before Magellan did it, but yeah.
Yeah.
Point still stands.
It demonstrates that aerobraking is a viable method for slowing down and for robotic missions.
Yeah.
Right? And so, basically MGS, because it's basically just Mars Observer but works this time, it has basically the exact same mission objectives.
Cool.
And a lot of the similar instruments that I think we're about to get into. But next slide, please.
Next slide, okay. I like this. I like this art, by the way. Concept art for these. Yeah, I like those.
Yeah.
The big paintings. They're nice.
I think this is just an image.
See, this is where the flat earthers are coming. Oh, we take a picture of itself.
What are you gonna? Yeah, let's add another 10 kilograms. Craft overview. So basically, this was built by Lockheed Martin Aeronautics in one of the plants in Denver, Colorado.
Yeah.
basically, I couldn't get a whole lot of stuff about the actual engine itself because all the documentation I saw just referred to it as the main engine.
Oh, okay.
But
You
I
can
know,
guess about 300 seconds.
okay, so about 300 seconds. But basically, it has gross liftoff weight of about a ton, 1 metric ton. The engine itself has a thrust of about 660 newtons, or about 150 foot-pounds of force.
Okay.
And it has 2 solar panel arrays, as you can clearly see,
Mm-hmm.
and those are charging 2 batteries. These things will become important later.
Okay.
Well, one sooner, the second later. Yeah.
Oh, fun.
But also, as you can see, it has drag flaps at the ends of the solar panels.
Yeah.
Because that's part of the whole aerobraking thing.
Yeah. If you look at old Mariner probes, you can see there's like paddles on the sides of the solar arrays.
Yeah.
Those used solar pressure to adjust attitude.
Oh, so doing a little solar sailing with those.
Yeah.
Awesome. This is going to be like the opposite of sailing.
Sinking.
Like parachuting.
Yeah, I'm parachuting. Well, sinking also, you know.
A little sinking, a little parachuting, you know.
Yeah.
Things that you want for your $154 million spacecraft.
It'll be fine.
Yeah, I'm sure it will. But now let's get into... Oh, yeah, also, there's a lot of instruments that are on MGS. But of course, there's a lot of different like relays and arrays and antennas where you can see the big high gain antenna up the top.
Guy. Oh, it's gimbals too. That's neat.
Yeah, yeah. And then also like the engine is like right behind the propellant tank. Yeah, it's like right there.
Yeah, it's a spacecraft bus here.
So basically it has to drain almost all like basically it has to shut off the engine before it can deploy the high gain antenna. But we'll get
we'll get there.
We'll talk about that later. Yeah. But for our discussion, there's really 4 major instruments on board.
Okay.
Let's get into them. Next slide, please.
Next slide. Okay.
Yeah. So, next slide.
Okay. So that's what we're looking at. These are all the different. Where'd you find this graphic?
It was on one of the NASA websites. It was like near the bottom of the page.
Oh, cool.
They had like a little 3D model of it.
That's neat.
Yeah. Shows a little bit of the instrument bay. So the first instrument we're going to talk about is the Mars Orbiter camera.
Cool.
Basically, it's a camera, but really it's 3 cameras all in one.
Ooh.
The first is a narrow angle lens camera, captures the black and white images. These are ones that are like up close and personal with the ground. Has a resolution of 1.5 to 12 meters per pixel.
Ooh.
Right. So basically, if you put your washing machine onto the surface of Mars, this thing could picture it. I mean, it'd be a pixel, but
You can see it.
you could see it. All right. Then it has a red wide-angle camera and then a blue wide-angle camera to get more like context images and like daily global images. Right. So the wide-angle ones basically say like, okay, you're getting this up-close image of something on Mars. Here's what it looks like around that at a lower resolution of 240 meters per pixel.
Okay.
And then one that's like 7.5 kilometers per pixel, just to get the global view.
Yeah. Mars is big.
Yeah, it's big. And of course, if you look at the image, there's Allen wrenches for scale.
Oh, good. So, yeah. Well, obviously, I gotta fix it, right? The little intern inside's gotta fix them.
I wouldn't trust an intern to touch this piece of machinery.
Oh, well, that's very mean of you.
Yeah.
Want to go to the next thing?
No. Well, one last thing I want to also mention is that this was developed by Malin Space Science Systems.
These guys.
Yeah, and they basically have made every single camera on basically any space mission since 1990.
So the guy.
Yeah, like Juno Cam, they made it.
Oh, okay.
Yeah. Also, Dr. Malin himself was one of the researchers for this mission, so...
Cool.
Yeah, I think. If I read that correctly.
Should I move to the next slide?
Yep.
Okay.
So, next up is the Mars Orbiter Laser Altimeter. Right, this thing is measuring the topography of Mars. So basically, it's just shooting down an infrared laser at the surface.
Yeah, and it reflects it back, and you can...
and it's just measuring the time then to give you the... basically say, hey, here's the topography.
Yeah, you're trying to figure out what this thing's shaped like.
Yeah,
Is it
exactly.
a billiard ball? Is it mountainous?
Yeah. And it has it's looking basically at a spot of the ground that's like, I think, 130 meters across. But it has enough vertical fidelity of about a foot.
Right? Oh, wow.
So if you had like stairs out on the surface of Mars, it could measure it. So it's pretty good.
Neat.
Next slide, please. So this thermal emission spectrometer. This is also one of the coolest things I've ever read about.
Okay.
Sorry. But basically, so one of the missions is to determine the composition of the surface of Mars. Well, how do you know what the rocks taste like from orbit?
Get a really long fish hook.
Yes.
You scoop them up.
Exactly. Well, basically, so you have the electromagnetic spectrum, right? You have ultraviolet light, visible light, and then infrared light.
Yeah.
Well, different materials reflect different wavelengths of infrared light. And so if you had a really bright infrared light source, like the sun, and it smacked into the surface of Mars and reflected that into the thermal emission spectrometer, right? The thermal emission spectrometer basically look at, okay, what are the wavelengths that are peaking, what are the wavelengths that are coming back, and they can use that to determine the composition of the surface of Mars.
Yeah, because you can, it's spectrometry, right?
Spectroscopy. Yeah.
So, spectroscopy. I'm not old enough to get one of those yet, but,
What?
Nothing.
Okay. But it also, because it's the infrared, because looking at the infrared spectrum, it's also can also measure like the temperature of the surface of Mars as well.
Yeah. It's pretty chilly.
Yeah. Well, actually, we'll get into that.
Oh, okay.
Also,
compared to Venus, it's probably pretty chilly.
I mean, compared to Venus, it's a refrigerator, but what isn't? Also, this was developed by engineers and researchers at Hughes Santa Barbara Research Center and Arizona State University, baby! Woo! I went to ASU in Tempe.
Yeah.
Yeah.
And I'm an engineer.
And you're here.
Yeah.
All right. Also, it was led by Dr. Phil Christensen, who worked on previous missions doing similar things. So he's kind of like the go-to guy for this.
Yeah, you discover there's a bunch of people who, it's like, oh yeah, he's this guy. You just point to this dark corner, he's over there.
There he is.
Go ask him. The music kind of rises, the spooky music. There's like lightning. It's like, what in the world's going on?
Yeah, you see that hooded guy in the corner of the tavern who's drinking alone? That's the guy you want to talk to. He'll give you the next quest.
Yeah. He helps you go to Mars.
Yeah.
Ooh, hey, water ice. Yeah, that's what you're looking for.
Yeah.
And then, polar ice caps. Those are pretty cool. Are you going to cover all these, or?
No, I was gonna say next slide, please.
Oh, yeah, these are interesting. Yeah, ozone.
I'd rather show you.
Oh, okay, fine.
All right, and then last up of the four is the magnetometer and electron reflectometer.
Ooh.
Basically, it's measuring the magnetic field of Mars, if there is one.
Yeah.
And of course, it's if you look back at the diagrams, which don't, but if you look back, they're way out at the end of the solar panels, because electromagnetism is one thing, So all the electronics in the spacecraft, have little wires with little currents running across it. They're generating ever so tiny little electromagnetic fields. Yeah.
I think we talked about it with Galileo too. That's where they're always just way out there.
Yeah, exactly.
So you can detect that.
Yeah, but still, you don't want any sort of interference whatsoever with that. So, that's really what I'm talking about.
So what kind of VGA adapters are these? I think I see these on some of my computers.
That's 90s technology.
Yeah, that's...
Let's move on. Next slide, please.
Okay. We're just going to keep going then? There's no dust counter?
Oh, we'll get to that.
Hey!
All right.
I know these pictures. I love these kinds of things.
So here we are. Here they are, packing up Mars Global Surveyor.
See, that's us right there. Right there we are, right? So I'm wearing my observer button, watching you do jazz hands or something, point at the...
I didn't realize I was not supposed to take a lot of the tape off of that particular component. So this is me trying to put it back on, and it's really bad.
And I'm judging you harshly.
Yeah, thank you. But here they are packing it up into the Delta II, so that way they can FedEx it to Mars, so that way the FedEx driver can carefully and precisely drop kick it into your front porch.
Yeah. I just noticed. So if you look down here, you know what those are?
What are those?
Those are spin motors. It's a spin table. So they can stabilize it, right?
Yeah, okay.
Yeah, so that's, again, see, there's the aerospace engineer coming in here to talk to you about the engines.
Getting distracted.
Yeah, so they spin it because if they have weird thrust performance, like asymmetric thrust on the solid motor, they can compensate for it.
Oh, okay.
And it looks cool, too.
Yeah. Spin it right up.
Yeah.
All right. Next slide, please. So they pack it up and they launch it on a Delta II 7925A.
That's what it looks like.
Yeah, at noon on November 7th, 1996, right? So they were aiming for that November 1996 launch window, and they were delayed by 1 day due to high winds, I think.
Yeah, that's the one thing. Can you imagine you have this big $154 million mission and the wind stops it?
Yeah.
That would suck.
Yeah.
Or like a hurricane hitting your launch site.
That would be pretty bad.
Yeah.
Yeah. But the first two stages of the Delta II kick it up into a 185 kilometer parking orbit.
Yeah.
Which is kind of low. But I mean, 35 minutes later, the third stage that you pointed out, the Star 48B, kicks on and kicks it on its way to Mars.
Yeah. And Delta II is going to do almost all of these Mars missions moving forward.
Yeah, it was selected because it was cheaper. Because the Mars Observer was launched on a Titan III.
Yeah, commercial Titan III. The last commercial Titan III.
Yeah.
The fourth.
Yeah. Next slide, please.
Next slide.
So, an hour after launch, the solar panels deploy. One of them deploys successfully.
Oh, no.
The other doesn't.
The Mars curse strikes again.
Yeah. It's continuing to strike. So basically when the solar panels are deploying, they're basically like doors, right?
Yeah.
They have a hinge and they're big panel. But of course, because space is a frictionless vacuum, if you give it too much momentum, it might snap off the hinges. And you don't want that.
That'd be bad.
Yeah, these aren't doors, these are solar panels powering your spacecraft. So they put in a damper arm to help slow it down, like a damper arm on pretty much any door.
Yeah, doors have those.
Yeah. Well, unfortunately, the damper arm broke on one of the solar panels.
So
basically,
this guy.
Yeah, a tiny little piece of it broke off and got lodged in basically like the hinge gap. It's like about a 2-inch gap. And so it prevented it from getting into an open lock position by like 19 degrees.
So it got stuck here, kind of like this diagram.
Yeah, I mean the diagram is really hard to see, but like it's not great because it's supposed to open up. If you go to the next slide,
Should we go to the next slide then?
Yeah, let's go to the next slide. So you can see from the different configurations, they're supposed to be angled at about a 30-degree angle.
Yeah.
Right? Except when it's in the launch configuration and put into the fetal position. But
Yeah.
it's meant to be locked into that open position because, next slide please, it's supposed to be doing aerobraking procedures, right? It's doing the Y of the YMCA.
Yeah, because air comes in this way then?
Yeah, because you can see nominal aerodynamic flow with a big arrow pointing up, right? So it's going engine first and the panels are swept back.
Yeah.
But, one of them is stuck in an unlatched position. The one on the left.
That's not good.
Yeah.
So this one's stuck.
Yeah, because it says broken damper centered on unlatched hinge on -Y wing, and the other one is plus Y.
Oh, okay. Oh, yeah, because it's got the coordinate system here.
Yeah. Yeah. So, here's my question to you, Mr. Structural Engineer Man. How do you fix it?
You wiggle it.
That was the first solution they came up with. They had two solutions. That was the first solution they came up with, right? And so they tried doing that in January and February of 1994. They tried wiggling it to shake it loose.
Because it takes, how many months to get to Mars?
10 months.
10 months. Oh, they took the long way, scenic route.
Yeah, yeah.
Yeah, you have plenty of time to shake this thing.
Yeah, so they shook it, and it did not get loose. It did not work.
Of course. Yeah, the easiest one doesn't work.
Yeah. So, how do you fix it?
Okay, so there's a piece of debris jamming it. How do you move the mechanical piece?
Yeah.
Do you do it during an engine firing? Because the engine should have more force.
But then you ruin the trajectory of reaching Mars.
But we could alter the trajectory as you come in. Oh, but it's got limited. We'd have to see the propellant, the Delta V budget.
For reference, it does perform Mars orbital insertion of 973 meters per second, but that's most of the fuel.
Yeah, that's usually what these do. How do you fix that? Would you do it in a specific like roll?
What do you mean by a specific role?
Like roll the spacecraft in a certain way, kind of like what they do with Galileo, trying to deploy the high gain antenna, or if you spin it. Also, this happened on one of the Soviet Mir modules, where one of the solar arrays didn't open, so they spun it, and then it opened. It depends. I'd have to see the mechanical configuration of the latch, like the. How did they solve it?
Okay, so I mean, hold on. Okay. Well, one of the things is that they have to because this is the aerobraking configuration, because it's doing like the Y of the YMCA,
Or raise the roof,
Yeah, it has to get into this configuration for aerobraking.
Yes.
Or does it?
Do they?
Because their second solution, next slide please, is to beat it into submission. Basically, instead of having it be swept up at 30 degrees, they're going to rotate it 180 degrees and have it pointing down.
Oh, so they're going to expose the solar. So they can turn the solar arrays, right? So they don't get heated, right?
Yeah.
Okay, so that's okay. So they put the important end that gets hit by the atmosphere first.
Yes. To
Bit of an
beat
issue.
it into submission, right? So to do this, though, they have to change a couple of things.
Yeah.
So instead of having the spacecraft is going to perform a burn that puts it into Mars orbital insertion, right? And that's going to be initially planned for 48 hours, right, in this large elliptical orbit that you see, right? So they decide to change that to 45 hours because they want to limit the amount of heat and pressure that the spacecraft is exposed to during aerobraking.
Yeah, because you're getting the important parts now.
Yeah, and because now they're going to be at a much lower capture orbit, they also changed the capture periapsis from 313 kilometers to 250 kilometers to reduce the delta V requirements. That way they don't use up too much fuel. All right, and so you can see what's happening, right? It puts it into a large elliptical orbit, not polar orbit, because you're mapping it, and then it'll use aerobraking to slowly get down over the course of 4 months.
Yeah, that's we do that with most Mars probes now too.
Yeah, this is the first one to do it.
Yeah, it broke.
And it's broken. So, next slide, please.
Ooh.
So, on September 12th, 1997,
So you're a
MGS
month
arrived. I'm a month old at this point.
Pretty excited, aren't you?
Yeah, I'm super excited because I'm a month old.
Yeah.
There's a lot to be excited about.
You're gonna get a button.
Yeah, I'm gonna get a button in 26 years.
Yeah.
Okay, so, MGS arrives at Mars. Next slide, please. So it begins. So orbit 1 does the Mars orbital insertion burn, right? That's the 973 meter per second insertion burn when it arrives. And then after 3 orbits, so on orbit 4, it starts doing aerobraking, right? So the periapsis is lowered into the atmosphere, and the broken solar panel is shoved into it.
Yep.
Right? And if you remember, it's broken by 19 degrees, right? So it's supposed to be latched at 0. It's currently at 19.
Mm-hmm.
So they keep pushing it into the atmosphere, right, with all these orbits and having the aerobraking occur. On orbit 11,
So this one.
yeah, the solar panel shifts by 4 degrees, right? So remember, it's off by 19, it shifts 4, so now it's 15 away.
Mm.
The next orbit, it moves 15 degrees.
Hey.
And you can even see in the comments for orbit 12, it says, is panel latched?
Yeah.
Yeah. And I think, hey, finally this is fixed, right? We beat it into submission.
Yeah. We got ya.
Yeah, we got it.
We broke the curse.
Not really, because it kept bending and shaking.
So it's loose.
Well, not exactly. They think it is latched. But between orbits 13 and 18, it's vibrating and it is bending still. So on orbit 19, they decide to take it out of aerobraking. They put it on hiatus to figure out, okay, what is happening?
Okay.
What do you think is happening, Mr. Structures Man?
Well, it could also been the stresses, it's going in a different way. Also, a different thermal environment because it's coming in differently. It's been in the wrong configuration for pretty much the entire flight.
Mm-hmm.
So it could have been bent out of shape. The sensors could be broken too.
Mm-hmm.
But what if they're detecting vibration though? That means it is shaking.
Yeah.
So that's not a bad sensor. You can detect that with roll rates and things like that.
Mm-hmm. Do you know what's happening to the other solar panel?
Oh, is that one broken now?
No, it's fine.
Oh,
It's
okay.
perfectly fine. It's acting as predicted. This one's not.
Is it just broken?
Not really. Well, kind of. Okay, next slide, please. So basically, the way that the whole solar panel assembly is attached to the main body of the spacecraft is through the yoke. You
This
see
guy.
the little thing at the bottom.
The box.
So they think that the yoke also broke during deployment of the solar panel.
So it's broken.
Yeah, so it fractured a little bit, and now because they're adding, the aerodynamic pressures and
Yeah.
temperatures for aerobraking, it's helping to make that fracture worse.
Yeah, it's not. Yeah, heating it up and shaking it does not make fractures better.
Yeah.
Trust me.
Yeah, I trust you. So basically, they decide, okay, so we have to reduce the we have to reduce aerobraking on this thing, right? We can't keep doing it where we're just plunging it into the atmosphere as harshly to try and beat it into submission. So they're going to decide to raise it up into the atmosphere, so that way it's being exposed to less atmosphere, reduce the pressure, reduce the temperature.
Reduce the stress.
Yes. But there's a problem with this. Because they're trying to put it into a 2 p.m. sun-synchronous orbit. So that way it's always orbiting Mars, always going over the surface at 2 p.m., right? Because the Project Science Group basically said that, all the equipment is optimized for that.
Yeah, it's better to take pictures. Probably better for the thermal environment too.
Yeah.
So
Yeah. You do 2 p.m., 2 a.m., 2 p.m., right? That's the orbit. The problem with this is because, number one, they put the spacecraft on a hiatus. It's going to be difficult to reach that in 4 months. And because now you're going to reduce the pressure on the spacecraft and slow it down, now you're probably going to miss it. So,
because it's a specific orbit because of the lopsided, because Mars is, it's because, similar reason on Earth, because Mars is a little oblate. That's how sun-synchronous orbits exist.
Yeah.
So it's specific.
Yeah. So, what do? Do you either risk the solar panel for the sake of the optimized equipment, or do you risk the mission for the sake of the structural integrity of the spacecraft? Which would you do?
Well, it's hard to complete a mission without a spacecraft.
Mm-hmm.
It depends on the margins, I think. How much power could you go without? With or without?
So which of the two options would you go with?
Well, I'd have to see all the reports on this. That's the thing. I'm not going to go, oh yeah, this one.
Okay.
What would you do?
Well, I don't have to answer that because I know the answer. Next slide, please. They decided to go with option 3. Wait longer.
Just wait longer? Okay.
Just wait longer, yeah. So that way, basically, they're going to hit it on the other side of Mars's orbit.
So they wait until they can do it again.
Yeah, so they break up the aerobraking into 3 phases. Phase 1 is the first aerobraking period. That's from orbits 37 to 201. Then they introduce a science phasing orbit, which is just there, hanging out, with an 11-hour orbit. From orbits 202 to 573, which is about 6 months long.
Yeah,
And then they're going to start up the second aerobraking period from orbits 574 to 1,325. So it added... So they were originally planning to do the primary Mavic mission in March of 1998. So that actually started in April of 99.
So it was planned to be right about here.
Yeah, because it was only supposed to be 4 months of aerobraking, and now it's about 16.
Yeah. That's interesting, though. There's a dust storm.
We're going to get to that.
Okay, gosh.
Next slide, please.
Hey.
So during the science phasing orbit, the spacecraft is there, and sure, the equipment isn't optimized for this particular orbit, but you could still use it.
You're still there.
You're still there, right? So they started taking pictures of the Martian North Pole, as well as cracking out the Mars Orbital Laser Altimeter.
Ooh.
Next slide, please.
Hey.
And so it could get a pretty good map of the North Pole. And Santa is not there, unfortunately. They couldn't map that.
Yeah, Santa Claus conquered the Martians. There's a documentary about this. It's stupid and bad.
Yeah. It's good stuff. But like, you can see the different layers inside of it.
It's kind of spiraling, too. You can see on this.
Yeah, it's a weird spiral formation. It's like higher and lower. And plus now, you could take all of this data and, next slide please,
Hey.
create a 3D map of it.
Yeah.
Obviously with a height exaggerated
It's
by like
it's exaggerated.
10 or 100.
Yeah. That's interesting.
But yeah, you can see it's all like lumpy and twisty and
Yeah.
weird. But pretty
Neat.
interesting.
Yeah, it's Mars. Mars is interesting.
Yeah. And it also took a bunch of other images while it was just hanging out and waiting.
Yeah,
Next slide,
chilling.
please.
Hey, Phobos. Hey, there it
Fear.
is.
Yeah, you can see how tiny
It
it
is so tiny.
It's a tiny little potato around a really big planet.
Isn't this like Stickney Crater the big one?
Yeah, it's huge.
Yeah.
On Phobos. I mean, look at that thing. It's tiny.
Oh yeah, but yeah, Phobos is cool. And aren't these lines here caused by tidal forces with Mars?
I think so, because that's like the only explanation. Like, yeah, what are these lines?
Yeah.
What are these doors?
We did this last time.
I know. It's still funny though.
We have to have recurring jokes, but not quoting movies. Gosh.
Okay, fine.
I'm just
So-
saying there's no dust counting.
No, we'll get to that.
Yes.
But you see, like, Phobos is pretty interesting, right?
Phobos is pretty cool. Yeah, there's actually been plans to put stuff on the surface. There's a Japanese mission coming up, the Martian Moons Explorer.
Ooh, that'll be exciting.
MX, yeah, that's coming up. I think the next window
When is the next window?
in 2026.
Oh. Okay, well, hey, we'll look forward to that.
Or is it this year? It's coming
I feel
up.
like it would be this. Okay. Okay.
Yeah.
So this is Phobos, but it also got an image of the other moon. Next slide, please. Deimos.
Deimos, the little guy.
Little one. You can see how it's a lot dustier and smoother.
Yeah, it is.
Than Phobos, yeah.
Now, which
There's
one's
so much-
closer?
What?
Which one's closer to Mars?
I think Phobos is closer.
Yeah, because it'd be tidal stress then. Yeah. Okay.
Yeah. But Deimos is definitely a lot smaller.
Oh yeah. Cute
Yeah.
little guy.
Yeah. But it also got an image of the Earth-Moon system and Jupiter.
Yeah. Which
There's-
Galileo's there right now.
Oh, yeah, yeah. When this
There
is... Yeah.
He's
It's
fine
there. Yeah, it's right there.
There he is.
There, right there.
Yeah.
Of course, this image is a little bit cropped because the actual image itself is more like the same dimensions as like the little margins off to the right of it, where it's like the
Oh.
moon and Earth are like way at the top, and then Jupiter's way at the bottom. But it's a great image.
Yeah. It's so
Yeah.
cool to see these kinds of pictures because you can still see sort of some features, right? You can see the reflection of the oceans.
Yeah,
It's really
you
cool.
can see a little bit of the limb of the atmosphere as well, as it gets like brighter towards the edge.
Yeah.
But also, you can see how the alignment of the planets from like the lighting, right? You can see how
Yeah.
Earth is basically half lit, whereas Jupiter's almost fully lit, because Jupiter's on the other side of the solar system.
Yeah. That's cool.
Yeah.
Hey, and we're in this picture. Doxed.
Oh yeah, we are.
Yeah,
we're both
we're-
alive.
Doxed. We've
Doxed.
been doxed on our own podcast.
Dang.
Oh no.
Oh dear. All right. Well then, let's move on to the next slide.
Ooh.
It even got Phobos eclipse on the ground.
That's cool.
Yeah.
Yeah, that's neat.
Yeah.
That's this kind of stuff that's kind of cool. Yeah.
Yeah. It's
So you know what these dark spots are?
So, if you recall, the color cameras for MOC, they're red and blue.
Yeah.
So the green is just kind of assumed, right? When you're putting the images together.
Oh, okay.
I think because of the high resolution, this probably was a black and white image that someone color corrected later.
Okay.
I think maybe, but those blue, I don't think it's actually blue. I don't recall.
Okay.
Because there were other images and comments about that I forgot, but basically it is because of like the
The camera works.
the way the camera works.
Okay, that's cool.
Yeah. Yeah.
And that's Mars.
That's Mars. That's the surface of Mars. So, after, 16 months of the 4-month aerobraking mission,
Yep.
the primary mapping can begin.
Ooh. Next slide.
Next slide, please.
Hey.
So the Mars Orbiter Laser Altimeter managed to capture a full map of the terrain, and this is shaded terrain map, right? Because you can see there's lighting with it.
Yeah.
Right? So lighting's coming from the top right, and then going down to the lower left.
Just like that.
Yes. And you can see that there are parts where it's really lumpy and other parts that are really smooth.
Because this is Hellas Planitia, I think that's called.
Yep.
That's HP. Here's the Tharsis Bulge, which is like this.
It's much bigger than that.
Yeah, it's huge.
Yeah.
There's Mariner Valley.
Yep. Actually, next slide, please.
Oh, you want to just go to the next slide?
Yeah, let's just let's get a little taste, right?
Oh, yeah.
So this is one with color added to show the altitude.
Yeah, you notice that the top part of Mars is kind of bald.
Yeah, notice it's also a lot bluer and thus lower than the rest of it.
Yeah.
There's almost like a big dichotomy between of the planet, right? Or like the lower half, the southern half is high, rough highlands. The north half is smooth lowlands, like low plains.
If I remember correctly, I read somewhere that the reason that is that way is because something the size of Pluto hit it. It just blew the crust off.
That would make sense. Yeah.
Because isn't this Olympus Mons or is this Olympus Mons? Or is that Olympus? I can't remember.
We'll get into this.
Okay,
So actually,
okay, we're getting closer. Okay.
Next slide, please.
Okay.
So you can see how they're like looking at a map of this. You can see that it's pretty diverse in its altitude and features. Right. You can see in the upper right, in the circle one, that's the North Pole we were looking at earlier.
So this is N.
Yep.
This is south.
Yes. Right. The South Pole also has weird spirally, like polar caps.
Yeah, that is weird. Those are CO2, right?
Yes, it is carbon dioxide.
Yeah.
Yeah.
That's neat.
Because again, there's like no water on Mars. But you can see, like in the lower image, right, with the altitudes. I know it goes from -8 kilometers all the way up to 8 kilometers.
Yeah.
But like,
Because you have to come up with a sea level. This is sea level, then you have altitude versus not. Earth, it's a lot easier because
there's sea there to kind of help. But look, with this one, you can see that the 0 altitude is at the yellow, which kind of defines the dichotomy between the north half and the southern half.
Yeah, because you can see it right with my yellowish
Yeah,
pen.
yeah, perfect. Easily distinguishable.
Yeah. There it is.
Yeah. So there's a couple of major features that you could clearly see from this map, right? The Tharsis Bulge,
Yep.
Tharsis Montes,
Yep.
the big mountains,
Yep.
Mariner Valley.
These
You
three
can
guys.
very clearly see there.
Yeah, which is, and then it's like the width of the United States, right?
Yeah. So in the ASU building I took you in, the science one, they had this giant mural, like it's like 20 feet wide, of Mariner Valley.
Yeah.
And they also included like this little scratch on the side, which upon closer inspection is the Grand Canyon.
Oh, jeez.
Yeah, the thing is probably, I think, 8 inches wide compared to the 20-foot model of Mariner Valley.
It's enormous.
It is giant.
That'd be really cool to see up close.
That would be cool. I mean, it's a lot closer to the East African Rift Valley than it is.
Because it's like opening up.
Yeah, that's tectonic.
Yeah.
Because think about it, you have the Tharsis Bulge right there. So.
Yeah, because you have a bunch of, no longer geologic activity, or at least muted geologic activity going on. But in the past, it's a lot more exciting.
Yeah. And then, of course, there's a couple of other basins, like the Hellas Basin, the big purple one.
This guy.
Yeah. And then Argyre Basin, which is that blue one right there.
The little guy.
Yep. And then also the Isidis Basin. That's the little one that's cut out above the Hellas. That's cut out of the dichotomy.
This guy.
Yeah, that one. And then there's also Elysium Mons, which is the one right
guy.
there. Yeah, the lone mountain over there.
Yeah, and I think where's Jezero crater, where the current rover is right now, the new one. I think that is somewhere I think it's over here in Elysium, like in this area. I think.
Okay.
I know there's a map you can find all the missions because you have because like they all kind of landed in these spots over here.
Well, we'll actually get to that.
Oh, okay.
So, actually, next slide, please.
Hey.
So, the Tharsis ball just really interesting because there's a bunch of dead volcanoes there.
Really big ones.
Really big ones. Like these are the largest mountains in the entire solar system type big. Like they make Mount Everest look like a joke.
Yeah, because isn't Olympus Mons the width of Maine?
Yeah, we're about to get to that. All right, so next slide, please.
Yeah, these are huge.
Yeah. So you can see that on the left is Alba Mons. This is the one in the north part of the Tharsis Bulge. That was, if it was still active, it would be the largest mountain in the entire solar system, but it's very dead and very old. Because you can see all of it is collapsing.
Oh, yeah.
Due to,
it's collapsing on itself.
Yeah, due to gravity, right? And you can also see all those stretch marks across it, right? Of course, these are exaggerated height maps. Yeah. It's a lot flatter.
Yeah, because I think if you stood on the top of like Olympus Mons again, you would not tell that you're on a mountain.
Yeah. We'll get to that. So I think this one is Pavonis Mons?
That sounds about right. That sounds one of them.
It's one of those. Yeah. And you can see that it has like the two like exit wounds kind of on either side, right? Where it's just spewing out material. And you can see like the material piled up around it.
Yeah, it's all kind of spilled out.
Yeah. And you can see the like very obvious caldera in the middle of
it's collapsed on itself.
Yeah, it's just like all of them have that.
That's so cool.
Again, these are all giant. Just
huge.
Giant mountains. But of course, next slide, please. The four largest mountains in the entire solar system, as you can see, it's from the over on the right, the top. That's the left. The other three, the other big three.
These guys.
Boom, yep. So that's so that's Ascraeus Mons is the upper right.
So that's this one. This is A.
Yep. Favonus Mons is the middle one. I think that's one we were looking at earlier.
Yeah, because it looks. I can see that it collapsed caldera. Yeah.
Yeah, and then there's also Arcea Mons, which is the bottom one, right? And like it is getting taller and taller and taller. Like the further down you go, the further south you go. But of course, they all pale in comparison to Olympus Mons.
Yeah,
that one,
the big one.
Yeah,
I want to be big.
Okay. Next slide, please.
Okay. Wait, it says 25 kilometers tall.
Let's move on.
Okay,
next
well,
slide,
good.
Please. Next slide. So this is Olympus Mons with a 3D model of it, and you can see that it is huge.
Yeah,
as you just said, it is 25 kilometers tall. For reference, Mount Everest is 8 kilometers tall.
So it is a little over 3 times the height of the tallest mountain on Earth.
Yes. But also, like if you were to stand at the summit of Mount Everest, you'd see the Himalayas.
Yeah.
If you were to stand at the summit of Olympus Mons, you'd just see Olympus Mons because it is 625 kilometers wide, or about the same size as the state of Arizona.
Oh man, Arizona's big and empty.
It is big
so
and empty.
So it looked like Arizona too.
Yeah. Well, I mean, there'd be a lot less trees and people, so it'd be a lot better.
Yeah.
But yeah, so because the height here in this image is exaggerated 10 to 1, it would look a lot more like, next slide please, flat.
Man.
This is the actual image of Olympus Mons.
That's so cool.
It's so big.
And you can see kind of it is still kind of sticking out. Right?
Yes.
You can see the kind of the cave canyon sides. I don't know what to call that. I'm not a geologist.
I mean cliff sides.
Yeah.
Cliff sides we work, and you can see where it's like flatter.
Yeah, outflow probably or dust.
Yeah, just because it's really old.
So. Yeah, because I remember in the Mars trilogy they terraform Mars, and the dominant thing that controls weather on Mars would be the Tharsis Bulge. It's that big.
It is huge. Like the Tharsis Bulge is 4,000 kilometers wide, so it's like the same size as the continent of South America.
That's huge.
It is huge, right? And this one mountain is the size of the state of Arizona, right? It's just everything's just scaled up.
Yeah.
It's really big.
Yeah. Big planet.
Really big planet. It was probably really hot, too, when this thing was active.
Oh, yeah. You're making these giant shield volcanoes. Because Hawaii, I think, technically is the biggest mountain on Earth. The big island is actually a giant volcano. It's actually it's actually taller than Mount Everest, but we don't count that because it's underwater.
Yeah. We don't like the water. We don't go under there because all the weird stuff is down there. So it's only what we can see when you take a picture of it, right?
Yeah, we do like topography and that sort of thing. But yeah, I think the biggest one on Earth is like Mauna Lea. I think it is. It's one of the Hawaiian islands.
It would make sense, right? Because it's actively building up. It's fresh and young. Because with the Himalayas, it's like constantly growing like an inch a year, but it's because two continents are slamming into each other.
Yeah, these are shield volcanoes, which they're just sitting there going, "Yep."
Yeah. And the Hawaiian Islands are also shield volcanoes, right?
Yeah, that's why Mauna Kea, I think, is the biggest mountain on Earth because of that.
Yeah, exactly. Right. But speaking of weather...
Ooh, what's weather?
Next slide, please.
Hey!
So, one of the things that the thermal emission spectrometer is also looking at is the daytime temperatures. And so the image on the left is summer in the northern hemisphere, and the image on the right is summer in the southern hemisphere.
So this is summer... Yes. I'm writing this. Okay.
Yep. So...
That's a bit different.
What do you know, and what stands out to you between these two images?
It's because Mars's orbit's more elliptical than Earth's, right?
Yeah. Earth from perihelion to aphelion is only different by like 3 million miles.
Nothing.
Yeah, nothing. Whereas Mars differs by about 25 million miles.
I remember reading so it's like southern summer, so it's cold enough in the winter that the dust in the southern hemisphere is like kind of bound with some of the water and the water ice, the carbon dioxide. Then in the summer it gets so hot it actually just sublimates into gas, which with the dust attached to it kicks it up into massive dust storms, if I remember correctly.
Yeah, so I was about to say that.
Oh, sorry.
Next slide, please. But also, if you notice, with these images, you can see that the high end of the scale gets up to 20 Celsius, or about 70 Fahrenheit. So, not bad.
Right now.
Yeah, really not bad during the summer in the southern hemisphere.
Yeah, okay. Yeah, so it'd be nice, kind of balmy, get out your t-shirt, shorts,
I mean, honestly, you can.
Yeah,
right?
You just suffocate.
You just, there's the lack of atmosphere, which...
this party sucks, man.
Yeah,
also fireworks.
Also, these are daytime temperatures, not nighttime temperatures.
They're probably way worse.
Yeah, it's a little different than that. But you can see, because Mars's year is about twice as long as Earth's year, right? You can see how it's like, these are almost like a year apart, right? Between the summer and the winter.
Oh, man. Eternal summer.
Yeah, I've been living in Arizona and Florida for the last 4 years.
I've been living in Alabama for the last nearly 5.
Yeah.
Okay.
Yeah. Hey, haven't had to shovel snow yet.
That's true. I haven't either. I've had snow, but...
Yeah.
Yeah, this is also
why you wouldn't have to shovel any snow on Mars because it's all just carbon dioxide ice. It's just dry ice.
Yeah, it's dry ice.
Supplement.
For your party.
For your party, it's perfect for the
Get the fog
brewskis.
machine. Yeah, get the brewskis, put in there. So you don't even need to make an ice maker. You just get some CO2 ice.
Yeah, you just get a bucket and a shovel and
put
some
of the cold ones in there, chill with your buddies.
Stick it in there, yeah. Mars, the party planet.
See, that's what you got to sell it as. Instead of none of this weird stuff that Elon's doing. He's got to sell it like it's the eternal party for about a year, and then it's, torturous cold.
Yeah, and really, really, really dusty.
Really, really, really dusty.
Speaking of which...
You want to go to the next... So we're going to...
Next slide, please. So one of the things the thermal emission spectrometer is also looking at is the amount of dust.
The most important thing.
Yes, the amount of dust in the atmosphere. And as you can see in the image, it's from June 11th, 2001. It's all very nice, very clear, almost no dust.
Yeah.
And then by August of 2001, it is very dusty.
That's a lot of dust.
That is quite a lot of dust.
So what's tau in this instance? Do you know what that number?
I don't really remember what tau is, but it's really dusty because next slide. What it was measuring was like the buildup of dust going on, and it basically just explained exactly what you were talking about.
Yeah, sorry.
Yeah, it's okay. But basically, looking at the map over on the right, you can see how it was pretty clear in June, and then it got really dusty into July. That was because, again, it's going into summer, right?
Yeah,
So
and it's just kicking up all of that. It's heating it up. It's sublimating. It's
kicking up all that dust. And so, next slide, please. It's covering the entire planet in a dusty haze.
Yeah. That actually reminds me, one of the first Mars orbiters, because United States Soviet Union, right, the big competition, the space race, we knew it was a big dust storm, and we told Mariner, I think it was Mariner 9, don't take pictures until the dust storm clears, because we could do that. But the Soviet Mars, I think, 8, they couldn't. So it took pictures of a dusty Mars. They couldn't see anything.
Yeah, it's dust. What are you gonna do? The only thing you can do with dust is count it.
Yeah, the most important thing.
That is the best part of every mission.
It's the
counting
only
the dust.
It's the only important thing you have to do in space. Just count dust.
Yeah, because
Wow, it's even called the 2001 Great Dust Storm.
I mean, I
You called it that?
It's just the 2001 dust storm because it was a couple of different dust storms that all kind of kicked up a crap load of dust into the atmosphere, and even though it never covered the entire planet, it did kick up a lot of dust into the atmosphere. As you can see from the image.
Yeah, that's a lot of dust.
The whole planet is covered.
Yeah,
except for like the South Pole. You can see how large the South Pole is.
Oh yeah, that's really big.
Yeah. So if we go to the next slide, please.
Okay.
You can see that it grows to a pretty decent size. Yeah.
Because it's seasonal variations, the big ones.
Yeah, because, again, Mars has a greater axial tilt than Earth does. And, of course, it moves in and out away from, both towards and far away from the sun. So you can see how it gets pretty giant.
But it gets to a nice 30 Fahrenheit.
Yeah, on the sun side in summer for the southern hemisphere.
So it's like living in it's the desert.
It's like the desert if the desert was really cold. It's Antarctica.
Yeah. Yeah, because it's the reason why tropical places stay hot all the time is because the atmosphere has a lot of water in it, and that keeps the heat. Whereas, not in dusty places with no atmosphere.
Yeah, I mean, with the Earth, it's also because of the Hadley cell, right? So
the sun's big giant.
directly. Yeah, it's directly over the sun is basically beamed down always on the equator, and there's a lot of water at the equator, so it evaporates the water and it hangs up in the warm air, right? And then the warm air ascends, dumps all the water, which is why it's all raining and tropical rainforests are at the equator. And then it heads north, where the air cools off and gets rid of all the moisture, and then descends south, which is why you get deserts at about 30 degrees north and south.
Yeah, I took a biogeography class. It was one of my first classes I took in college. It was really cool.
Yeah.
Yeah.
It's fat. It's good stuff. But yeah, you can see how big the poles get. And it's all carbon dioxide.
Yeah. So don't breathe that, kids.
Or drink it. Don't do any of that.
That would be bad.
Yeah. But also, getting back to the most important part of the mission,
Dust.
Next slide, please.
Look at that dust.
Yeah. So most of the actual dust storms that occur on Mars are in the northern hemisphere.
So the North Pole's right there then, right?
Yeah, but the whole white part is the extent of the ice.
So the giant seasonal shifts.
Yeah, that's winter.
Yeah.
For the northern hemisphere, right? But you can see all the dust storms forming, and over on the right, you can see the
this guy.
Yeah, vortices, right? You can see like polar vortexes occurring, like right next to the pole.
Because it's what it do. Because it's atmospheric dynamics.
Yeah, exactly.
So cool.
It's very similar to Earth.
Weird.
Yeah.
Atmospheres behave like atmospheres?
That's bizarre, right?
Weird.
Weird.
It's weird, bro.
Okay, so now I think getting back to the most important part of the mission.
Well, dust. We're still doing dust here.
Yeah. Next slide, please.
There we go. That's interesting.
Yeah, so again, the thermal emission spectrometer, it is looking at the composition of the surface of Mars, but also its abundance, because it's mapping it, right?
Yeah.
You can see the mapping marks across this entire map.
So there's a lot of surface dust. There's one surface dust, a lot more in the northern plains.
Yes.
Than there are on the southern parts.
Yeah, because the north is, again, just a giant,
Bowl.
smooth plain. Yeah, it's basically a giant bowl.
You can also see the giant volcanoes.
Yeah, you can see the Tharsis Bulge very clearly, right? There's the three main Tharsis Montes. You can very clearly see Olympus Mons, and you can also see Alba Mons kind of up above it.
Oh yeah, there's these guys.
Yeah, that's Alba Mons, and then the other one is
That's Olympus, and then there's Elysium, right?
Yes.
Good, I remember this.
Yeah. And so thermal emission spectrometer. Next slide, please.
Also, there's the Hellas Planitia.
Yep. Next slide, please. You can also see that it's looking at the other materials on the surface.
Because pyroxene, plagioclase,
Silicates.
Yeah, Yeah, because that's again what Earth's made of too.
Yeah. And hematite, which only exists in one spot, it looks like.
This is where the Minnesotans will move to mine iron ore. We'll build our own Edmund Fitzgerald there.
Exactly. Also, you did point out the Hellas Basin before, but you can clearly it's like the Greenland of material science because there's no data coming from it.
Yeah. It's interesting to see. You can see a lot of pyroxene plagioclase in these spots here. I forgot the name of this. What place is that?
I also forget the name of that.
Because this is the Tharsis Bulge here.
Yep.
Because there's not much. You can see there's a lot of silicates up in the north, too.
Yeah. You can also see how almost none of these intersect with the dust either.
Look at it, because maybe the dust is covering it.
Yeah, probably.
That could be it. We're not geologists, so...
Yeah. Also, you can see the detection limit kind of closely.
It's got some limitations. So that could be that
anything anything below the green, it's like we can't really detect.
So there could be a lot of it. They just don't see it.
Yeah, exactly. It could be a lot hidden below the dust as well.
Yeah. That's cool.
Next slide, please. Oh, yeah. Okay. So Mars' gravitational field.
I noticed a few themes here.
Yes. But first question is, how do you measure Mars' gravitational field?
I know on the Grail mission for the moon, they had two spacecraft close to each other, and they had lasers between them, and they can measure that. The changes.
Oh, that's pretty cool.
Yeah, we'll talk about those because they use the ballistic capture trajectory also.
Nice.
It's because it's gonna be Doppler, wouldn't it be? It'd be changes. Oh, I used to know. I used to know this. I'm really close because gravity. You can detect the changes in gravity based on orbital mechanics and based on your equipment. I just don't remember the specifics.
So I found like one sentence that explained this. It really didn't explain it. But yeah, you basically, if you assume that Mars is a point mass and you know the distance from the center of Mars to your spacecraft,
which you can measure,
which you can measure, right? And you know the orbital velocity of your spacecraft. Right, they'll give you the orbital. They'll give you the mass of Mars.
Yeah, because it's a gravitational constant used in the calculation of orbital mechanics.
Right. But Mars is not a point mass.
It's a lumpy mass.
It's a lumpy mass. The mass is distributed unevenly.
As you can see.
Right, and so this is going to cause changes and alterations and minor perturbations in the spacecraft's orbital velocity. And the way you measure that is because your spacecraft is constantly talking with Earth. It's sending back radio transmissions.
Doppler.
And so, you can measure the Doppler effect within those radio transmissions and use that to calculate the tiny variations in the spacecraft's orbital velocity. And because you're in a polar orbit orbiting the entire thing, you can map out the gravitational field.
So it looks like these mountains are big and heavy.
Yes, you can very clearly see the Tharsis Bulge and Mariner Valley and the individual mountains.
Yeah.
Yeah, you can see Olympus Mons, you can see the Tharsis Montes, you can see Elysium, you can see the big basins and craters.
Yeah, there's Hellas again.
Yeah.
That's neat.
Also a neat thing that you could do is you could start combining data.
Ooh.
So, next slide, please. If you were to take the MOLA topography, combine it with the gravitational field map, you can determine the thickness of the crust.
Nice. So the crust is really thick under the mountains.
Yeah, under Argia
Yeah.
Mons.
Right? Yeah, that's really deep there.
Yeah.
And it's not very thick in the northern hemisphere.
Yeah, I wonder why.
I wonder why. Oh, there's also some spots here near Olympus Mons.
Yeah. But also, well, speaking of the crust,
Yeah.
remember the whole magnetic field thing?
You can measure that.
Yeah, you can measure the magnetic field. So, next slide, please. So, Earth has a big planetary magnetic field generated by the dynamo effect happening inside the Earth, right? It's big, hot metal turning fast.
Really fast. Fluid Dynamics 101.
Yeah, and it's creating this huge electromagnetic field.
I thought we'd just start quoting the core.
Yeah, no, I'm gonna move on. Sorry. Mars doesn't have that.
Oh, that sucks.
Yeah, but what it does have is these really powerful crustal magnetic fields.
Cool.
These really strong crustal magnetic
Because
fields.
it's iron.
Well, actually, it's a little bit more complicated than that.
Oh, sure.
So you can see, like, day 264, right? You can see it moving in, and it has, like, 400 nanoteslas.
Yeah.
That's what it's measuring. You can see that there are these local crustal magnetic fields across the planet. And because you're in orbit, you can measure it.
Yeah.
You can map it out. So, next slide, please. This is actually from a paper by Connerny et al. That was published in 2005.
Yeah, that's what's
that shows. Yes, there's a citation, and it shows the full map of the magnetic fields on Mars. Now, do you notice something?
It's a big concentration down here. So that's Mariner Valley. So that's Hellas.
Mm-hmm.
So there's a big. So let's see. So the nanoteslas are per degree. And B is magnetic field, right?
I
think that's what they use for magnetic field. I'm just having.
Well, it's measuring the
flashbacks.
magnetism of the planet, so it's assumed that's what it's measuring.
Yeah, so there's a lot of magnetism there in that spot between down there near the south pole.
Near the southern.
And there's also some up here just for some reason.
Yeah, but what do you notice about the shape of these
Stretchy.
different patterns? Yeah, it's kind of linear, right?
Like an impact.
Not like an impact.
Oh. Stretching.
Mm-hmm. What kind of stretching?
Tidal?
Not tidal.
Crust shrinking.
No. Other way.
Crust expanding.
Yes. So there's a similar effect to this on Earth, where if you look at like the Mid-Atlantic Ridge, if you were to
it lines up differently, right?
Yeah, well, it lines up linearly, right, going out. Basically,
Yeah.
it's like a rotating dynamo, and so you
Right.
get North Pole and then South Pole and then North Pole and then South Pole. Exactly.
Yeah.
So what does that tell you?
Magnetic field changed a lot. Flips.
Yeah, it flips. But what does that also tell you about what was happening on Mars physically?
It had a magnetic field and internal dynamo at some point.
Yes.
And it
What
flipped.
was also happening on the ground, to the ground.
Tectonic activity. And there was expansion in rift valleys and things like that.
Exactly. So, like 4 billion years ago, Mars is pretty similar to Earth, or 3.5 billion years ago. Mars is pretty similar to Earth in that it had, an internal dynamo, had a planetary magnetic field, and had plate tectonics occurring. But then it cooled off pretty quickly because there's a
small.
lot less Mars. Yeah, it's pretty small, and the convections of creating plate tectonics
it's dumping
cools it
heat.
off faster.
Yeah.
Yeah, it's dumping heat.
Because Earth's going to lock up in about 7 billion years, if I remember correctly.
A lot of things are going to happen in 7 billion years, but me being alive is not one of them, so who cares?
Not with that attitude.
Yeah. So basically, it probably had this big crustal rift in the southern hemisphere, generating generating new crust down there.
Yeah.
Right, having these rotating dynamo effect, right, creating these crustal magnetic fields, and then because it cooled off, plate tectonics stopped, internal heat stopped,
Yeah.
and the planetary magnetic field stopped.
Goes away.
And this is all that remains. And of course, these magnetic fields are like 30 times stronger than Earth's magnetic field.
Oh.
So, pretty powerful.
Oh, okay.
Yeah.
Hard to navigate on Mars, then.
Yeah, you can't use a compass.
No. You could, you wouldn't go to the place you want to.
Yeah, the compass would bring you to a random location.
Yeah. It just consistently takes you to the wrong place.
Yeah,
There's
it's
guys who
always the
set up
same.
like hot dog stands there. It's like, hey, you guys lost again.
Exactly.
That's what we break out great. You bring your CO2 ice, the brews, you know.
Yeah. And there's a guy with a hot dog stand on Mars.
Yeah, that's what Darren McGavin wanted to make in the Martian Chronicles.
Oh, okay.
If you remember, I know you don't remember that.
No, that was like 20 years ago.
Those sucked.
Yeah.
You want to go to the next slide?
Well, the next slide talks about or shows a little bit of like how the southern hemisphere is a lot higher than the northern hemisphere.
Yeah.
Right, you can kind of see that the Martian dichotomy.
Martian dichotomy.
Yeah. Next slide, please.
Hey.
Yeah. So another thing that keeps happening on Mars is that these little tornadoes, these little dust devils, crop up. So basically, it's just the winds, acting like a tornado because there's so limited little atmosphere. It's just a light dust devil.
I think one of the Mars rovers actually got hit by one once.
Yeah, I think that would make sense.
At that point, they've been on Mars so long, they probably would have been hit by one.
Yeah. Yeah, they're pretty common, right? And as you can see from the middle image, right, you have the dust devil. It has like a shadow cast from it over to the right, but then it's also leaving a track.
Oh, cool.
Yeah, because as you see from the image on the right, basically as the Martian soil just sits there baking in the sun, it gets lighter. But then when a dust devil comes along and churns it up, you have the unexposed younger soil that's darker on Mars.
That's cool. That's called regolith.
Regolith. I'm going to use that term now.
Because regolith on Earth, yes, is a lot of carbon in it from dead stuff.
Oh, okay.
Right, that's why, if you look at, that's why like dirt here is more reddish because it's actually iron oxide, but up in Minnesota it's a lot more brown and rich with carbon and dead stuff in it.
Ah, okay.
Yeah.
So the regolith on Mars, the undisturbed stuff that's baking in the sun is lighter, and the regolith that has been disturbed is darker. Right? And you can see these dust devils come in different shapes and sizes and going on different paths, right? Some are really thin and small, others are really thick and powerful.
Yeah.
Right? So, next slide, please.
Ooh.
So, as we talked a little bit earlier, when it comes to like the poles and ice on Mars, it's carbon dioxide, it's dry ice.
Yeah.
Right. Yeah, and because of the conditions on Mars, it doesn't melt. It just skips straight over to evaporating.
Yeah,
that's sublimation. Goes from solid to gas immediately. Right. So you can see over in the left image, the lighter areas are the dry ice, and the darker areas of where it's been sublimated and exposing the regolith.
And that's what's going on in the middle image then?
So the middle image, the middle image is going on in the southern hemisphere. And you can see that it leaves these weird shapes behind, like these really weird. I don't know why they have these weird organic round shapes. It's really weird. On the far right, you can see that it's like a close to true image or true color image, where it's bright white with the dark brownish red regolith sublimating, or the regolith being exposed after sublimation.
Yeah, that's weird.
Yeah, it is weird that the formations that it leaves.
Yeah.
So the southern hemisphere leaves these weird patterns, but in the northern hemisphere, next slide please, you get these dunes, right? Because of all the dust that's up there.
Oh, and it makes dunes because it's the wind and the...
Yeah, because of the winds and the solar vortices, polar vortices. And
that's the older regolith then.
Yeah, so you can see from left to right, the dunes sublimate first, right? So you can see them sublimating first, and then from the middle image, you can see that they have sublimated fully with the ice still on the ground. And then over in the right image, you can see that afterwards the ground starts sublimating after the dunes.
Neat. Probably because the dunes have less thermal mass, so the sun heats it up. Those heat up faster.
Ah, okay, yeah.
Because the ground takes a while to heat up because it's big. Dunes are small. Those heat up faster.
Yes.
That's why bridges freeze before the ground does in winter.
Oh, okay,
that
makes
thing
sense.
You haven't experienced in 4 years.
Yeah, It's really nice. So, next slide, please.
Ooh.
You can also see some lava flows that were taken by the MOC. And you can see that, like, over on the left, there's, this tiny little baby volcano. You can see the little caldera of it.
Yep.
That's now, no longer active. But you can see the lava flowing that have flown out of it. It's kind of got that weird, pointy drywall texture to
like
it.
your ceiling. Like
Yeah.
popcorn.
Yeah, exactly. So you can see how it was flowing in the past of the middle image, right? It was like flowing out and
like lava.
And splaying like lava. Yeah.
Well, with a thinner atmosphere too, probably it would evaporate differently, cool differently.
Yeah, probably would. Yeah. And of course, over on the right, you can see it kind of flowing into some more valleys and some gullies there. I think that one's from near Olympus Mons, or at least the Tharsis Montes.
Neat.
Yeah. Next slide, please. So you can see that there's a lot of evidence that there was a lot of water on Mars in the past.
Yeah.
You can see these ancient rivers. You can see like the flows over on the right. You can see like the channels in the middle and like the weird river shape to them.
The deltas
over on the right.
Yeah.
Yeah.
That's cool.
And next slide, please. You can see that there were ancient river deltas that went into these giant craters and canyons.
Yeah, and that's where the one is right now, Perseverance. It's in one of these old river deltas. It's looking for stuff.
Okay, yeah. I mean, that'd be a great place to look, because a lot of stuff flowed in there back then.
Yeah.
Back in the day.
Yeah.
And of course, this is a small scale example. If we go to the next slide, please. Large scale is that Mariner Valley just empties out into the basin, into the northern plains. Yeah, exactly. Right? You can see like the very clear river shape. River delta.
Wow,
and the topography.
Yeah, that's cool.
Yeah.
Mars is neat.
Mars is neat, but of course, there's no water on it left anymore. So it's this is all just ancient stuff. Now it's all next slide, please.
Party's over, man.
Yeah, now it's all just erosion through wind and gravity.
Big landslides.
Yeah, you can see these big landslides, right? You can see the spurs and the gullies. You can see how it looks very Earth-like.
Oh, yeah.
Right, you look at like mountains or cliff sides or canyons or anything like that. This is what they look like.
Yeah, we're in the Grand Canyon. There's stuff that look just like that.
Yeah, about the same color too.
Yeah.
Yeah, and you can even see like some sublimation occurring over in the right image.
Oh yeah, there it is.
Yeah, but it is all just like wind and gravity. That's all you need to.
Well, that's all you have left.
Yeah, because there's no water. Next slide, please. Right, and so you can see like all of these different like landslides and gravity and wind just like cutting into it and sloping it down.
Yeah, it does tell you when these recur.
Yeah, all seasons, late winter, early spring. All seasons, early spring. I don't know which. Oh, it wouldn't be hemisphere dependent, because it'd just be in that hemisphere, the season for that hemisphere. Yeah. And so, next slide, please. You can even see how, like with the dust devil, how it would kick up the younger, darker regolith
compared to the landslide would expose it.
Yeah, exactly, right? So that's how you get these dark shapes, right? And over on the right image, you can even see some of them in a quote-unquote true color image from this, right? Yeah. And this is all due, again, it's all due to just wind and gravity, right?
Yeah. I mean, what else would do it? Martians? Santa Claus kicked them out.
Well, next slide, please. See, one of these gullies, or actually a couple of these gullies, was photographed. This one was photographed first in 2001.
Right there.
And then again in 2005.
Right there.
What do you notice?
Something eroded.
Something eroded, right? The one on the left is dark, but the one on the right is bright.
That's not right.
That's not right? Remember what we discussed?
Yeah, it should be the other way around.
Younger regolith is darker. So why is it brighter? Also, why is it splayed out when it hits the canyon or the crater floor?
Fluid.
It's a fluid.
It's liquid.
It's a liquid fluid, right? But obviously, it's not water.
Yes, it is.
Right? Next slide, please.
It's ethanol. It's your brewskis. You spilled them, bro.
So, a bunch of these gullies have been photographed and documented, and as you can see, there's some underground liquid fluid that has to be creating them. Because, like with the image on the right, you can see that it didn't come from the impact crater.
Yeah.
Because you can see the erosion is a lot fuzzier and softer.
But this is down.
Yeah, but that, you can see, there's also no connection to the top. So it's not like boulders or sand or anything. So some liquid under the ground would have to have moved it and eroded it.
Yeah.
But it's probably not water, because again, it's
the brews.
No water on. It's the it's the brewski.
You spilled it, man. Spilled it, bro. Ruined the vibe. I'd go drive to get more, but I don't know where to go.
This compass doesn't point north.
Oh, sorry.
So, go back, please, one slide.
Sorry.
It's okay. I mean, basically, the only way that you would actually be able to find water on Mars is if you put something down with another mission. So let's talk about some other missions.
Yay!
So, Mars Global Surveyor became the first spacecraft to ever photograph another spacecraft outside of Earth.
Yeah.
Yeah. So you can see Mars Odyssey is over on the left, and Mars Express is over on the right.
And Mars Odyssey's got a big old thing on the end, because these are solar panels, and this is the big dish. Actually, my Lego Delta 2 came with Mars Odyssey and one of the rovers. Yeah.
Oh, cool. And there's also Mars Express over on the right, which that could also be aliens.
He's pointing at you. It's like, you.
It's
It's
got a really long finger, yeah.
You spilled the brewskis.
We're coming after you for the brewskis. But also, next slide, please.
Hey!
Part of the Mars Global Surveyor mission is to survey for future missions, right?
Yeah, it's Global Surveyor, because they're building up to hopefully human Mars missions in the early 2000s or about now.
Yeah, right. And again, it's all part of planning out future missions, right? Yeah. So here we have Spirit and Opportunity, which were 2003, landing in 2004.
I remember that, because I remember in 4th grade, a teacher gave me a Smithsonian magazine about them. I've left it on my desk.
Awesome.
He told me to leave. Freak.
But then also planning for a Phoenix mission to launch in 2007.
Oh, that's the one in Breaking Bad.
Yeah, we'll get to that in a second.
Okay.
We'll get to that in a second. So next slide, please.
So
it started helping out, looking at some of the landing sites that you can see from this MOLA image.
Yeah.
All right, so there's Opportunity in the middle, Spirit over to the far right, and Phoenix up to the upper left.
Yeah, they are looking. Spirit and Opportunity are in that green sea level area.
Yeah.
And Phoenix is just way up there.
It's way up there. It's polar lander, or a replacement for the polar lander that didn't work.
The one that crashed with Mars Climate Orbiter.
Yeah, probably.
It exploded.
Next slide, please. All right, so part of helping to Opportunity to figure out where to land, it's also looking at hydrated minerals as well as clays. And hey, there's a good concentration right where, in the blue and the green, saying, hey, put Opportunity here.
Yeah, this spot.
This
interesting thing.
Yeah, because there's there's the dirt to smell.
Yeah, go sniff some dirt.
Yeah, exactly. Next slide, please. And it even was monitoring the weather for these missions, right? For these landing sites.
Yeah, so,
right?
So you can plan them.
Yeah, the whole plan. It was like, hey, with Gusev crater, it's
this one.
Yeah. Yep. No, this one on the left.
Yep. It's a Gusev.
And then the
G.
Yeah. Then the Meridiani to the right. Right, and it's gonna be dusty for Meridiani, and then pretty clear over Gusev.
Yeah, we've got some clear skies over in Gusev. Good traffic report back to you, Steve.
I mean, look, this is a weather report, right?
Yeah.
The skies over Gusev should continue to clear during the next week, while storm activity along the Chris storm track should keep the skies over Meridiani dusty, right?
I think it's Crazy storm track.
That's my bad. I'm so sorry.
It's okay. Again, it's when you read a word, you form it in your head, and you've never said it before.
Yeah. It's weird. I can only extrapolate based off of the stupid English language.
Versus the smart English language, or
Versus
the
the smart English
or the
language.
really stupid English language, the above average, but I skipped some classes English language.
Yeah, exactly. Next slide, please. And so it's also helping to track the Spirit's mission from the Columbia Memorial Station, from where it starts, all the way out to the Columbia Hills region.
Oh, Missoula? Oh no, isn't that in Montana?
Maybe?
I think that's
I don't know.
I think that's where there's a university there.
Okay, so it's probably named after the university.
And of course, Columbia's Memorial Station is
After Columbia.
Yeah.
And for opportunity, it's Challenger.
yeah.
So
I think they named some of the mountains after the crew.
that's nice.
Yeah.
But you also see it. Look in the image. You could see some tracks from dust.
Oh
Dust
yeah,
devils.
yeah, they are.
Yeah.
And so what's the blues and reds are those of topography?
Yeah.
Okay.
That's from topography.
Okay.
It's overlaid.
Okay.
Right? And you can see it's pretty short distance to cover 160 souls.
Yeah.
Because you can see this 400 meters. So that's like a 30-minute walk.
Yeah, but these things are pretty delicate.
Yeah.
Do you ever see? Because you can see video of this at JPL when they do the testing of the rovers as they're rolling them, roll them. It's really boring.
Yeah. They move so slow.
Yeah.
Yeah. But hey, they're doing good work.
They
So
did some good work on Mars.
yeah. So next slide, please. And so for the Phoenix landing site, it's surveying it, right? Taking a look at it,
Yeah.
seeing what's there, right?
So I'm assuming this is where they want to land it.
Yeah, either that spot or the other harder to see ellipse.
This one.
Yeah, that one.
So that's
And you can see, kind of up in the upper left corner, there's the south. No, that's the north.
that's
Pole. Is
north.
that the south?
Yeah, it's North Pole.
Yeah. Okay.
Yeah, because you think about it, they want to land somewhere flat.
Yeah, and North Pole. North half of the continent's
Yeah,
perfect spot.
the north half of Mars, kind of flat.
Yeah. Wait, no, this is south. Look, it says 78 degrees south, and that is the South Pole.
Oh, okay.
That's weird. Because if you look at next slide, please.
Okay, so okay,
They're actually looking at the North Pole,
yeah,
which is really weird.
it must be the labeling scheme.
Probably, I don't think so. But either way, you can kind of see how it's like they were measuring. You're looking at molar topography, seeing the differences in elevation, and even looking at the temperature over in the far right. You can see how that's Kelvin, right? So 275 is freezing.
Yeah.
275 Kelvin.
We also want to design your thermal systems for your spacecraft based on where you're going to be,
Yeah.
right?
So you want to make sure that it doesn't freeze.
Or melt on Venus.
Yeah.
Yeah.
Yeah. So you can see that it's like trying to help out these other missions.
Yeah, you use them. You have spacecraft there. Use them.
Yeah, use them.
Weird. What a weird idea.
Yeah.
Because I know Lunar Reconnaissance Orbiter takes pictures of the crash sites of all the new lunar landers.
How? Imagine crashing your spacecraft and then another spacecraft like flies by and starts taking pictures.
Take a little selfie.
Yeah. Oh, look at
this
you
train
can't
wreck,
park
bro.
there, sir.
All right, you want to go to the next slide then?
Well, unfortunately, so from the research that I did into this mission and the few little research that I did in other Mars missions, I've learned that Mars missions are a lot like hamsters. They don't die quietly.
Oh, I thought they eat their young.
Do they eat their young?
I think when they get panicked, is that our hedgehogs? There's one,
Hamsters are weird.
yeah, yeah. Who knew?
Next slide, please.
Okay. Uh-oh.
So
I see error.
Yeah, so in June of 2006, almost a full 10 years after it was launched,
Yep.
A programming error happened. Basically, they were trying to They were trying to write a code of where the high gain antenna should point during a contingency problem, but they wrote it into the wrong part of the memory on the computer, and so they overwrote the controls of the solar panel limits and corrupted the pointing direction of the high gain antenna for a contingency. Then in November 2nd of 2006, just 5 days shy of the 10th anniversary of the launch, there was a command sent to reorient the solar panels, but the solar panels tried to move beyond the limits, their physical limits,
yes.
for where they could move.
Stretching too far.
Yeah, and so basically it threw the entire spacecraft into panic mode because it doesn't want to destroy itself, and so it defaulted into a contingency.
Oh no.
The contingency oriented the spacecraft in a really weird orientation. It pointed the high gain antenna away from Earth and exposed one of the batteries to direct sunlight.
That's not good.
One of the two batteries, right?
Mm-hmm.
So because it was being, if you know anything about batteries and temperature don't mix.
Well, they do mix if you don't like batteries.
Yeah, exactly. So because one of the batteries that was being exposed to direct sunlight started overheating, the computer misinterpreted that as it was being overcharged, and so it basically just cut it out, right? It stopped charging that battery. It's like, yeah, just stop using that battery. But the other battery could not handle the electrical load the other instruments of the spacecraft were using.
Oh, man.
So over the course of the next 6 orbits, the battery slowly drained.
And it's pointed the wrong way.
And so on November 2nd, 2006, we get to the end of Mars Global Surveyor.
Oh, let's give a little salute for it. Salute this
Next slide, please.
Okay.
End of mission.
We salute you, Mars Global Surveyor.
You did good work.
You actually worked.
10 years. It spent almost 10 years in space.
Yeah. It would have, if it was still operating today, it would be the longest surviving spacecraft around Mars.
Yeah.
The record right now is 2001 Mars Odyssey. When do you think that one launched?
Well, we saw that was in 2003.
Yeah. And they're actually going to kill it next year.
Really?
Yeah. It's because it's old.
Yeah.
It's really old, but...
It's 20 years old, yeah.
Yeah.
Yeah. But, I mean, it had...
It's a lot.
It did a lot. I mean, so it was the first mission for the Mars Surveyor program. You know what happened to the Mars Surveyor program?
What happened to it?
You know what happened to it?
It went to the Mars Pathfinder program, right?
No, it went to the Mars Exploration program. Right? So the whole thing became Mars Exploration program, of which there's a bunch of missions for it.
Yeah, like the rovers,
it's still
right?
going on to this day.
Yeah.
Right? Since Mars Global Surveyor, we have had a constant presence at Mars with orbiters and landers.
Yeah, that was the plan, because it would be put an orbiter and then put a lander every opportunity.
Yeah, every 2 years when the launch window came up. And yeah, it has been massively successful because of that.
Yeah. Well, except for the
really...
first two, Mars.
Yeah, well, I mean, after Mars Global Surveyor, mostly.
After Mars Climate Orbiter.
Yeah. Yeah.
Whoops.
But, I mean, it has an ongoing and continuing legacy.
Yeah.
Because it helped to set the foundation for the Mars exploration program. And all the successes, all the way up to, putting the first helicopter on Mars.
Yeah.
And having the first flight on Mars. That would not have been possible without Mars Global Surveyor.
Yeah.
Yeah.
And when we do finally send humans to Mars, it'll be partially because of the work done on these missions.
Yeah, exactly. But in a more direct sense, next slide, please. So, remember that Phoenix lander?
Yes.
That Phoenix mission that this thing was helping to survey the landing of?
I see 2 white splotches here.
Yeah.
It was digging.
So, Phoenix lander launched in August of 2007.
Yep.
And landed in March of 2008. And it dug up samples near the North Pole of Mars from the ground.
Because that's where you'd find ice.
And, well, in July 31st, 2008, NASA officially announced they found water on Mars.
Yeah.
Yeah.
There's water
Would
on
have been
Mars.
possible without Mars Global Surveyor.
Yeah. Woo.
So, yeah. That's the ongoing and continuing legacy of Mars Global Surveyor.
Yeah, the first successful Mars mission since the Viking landers.
Mm-hmm.
And a massive
one that
gap.
started the Mars exploration program
Which-
and everything since then.
Which that is a good program organization. Because that's actually one of the big things of the early 90s in kind of how we did space missions planning after that. Because we looked at things like Galileo, which cost a lot of money and broke. It's how do you classify and stratify missions for funding? Because we can't keep doing Galileos, but we also want to do a Galileo, right?
Yeah.
Or Mars Global Surveyors, faster, better, cheaper. I think it's the prototype for the Discovery program. I think it is now, or something like that.
Okay.
Yeah,
Yeah.
that's water.
That is water. That is water on Mars. Yeah.
And that's when in Breaking Bad,
Yeah.
and when Walt talks to what's his face, Jane's father.
Yeah.
That's what they're talking about. That's why the episode's called Phoenix.
Yeah.
That lander.
Yeah.
That's cool
Yeah.
because it's on Mars. There's ice.
Because yeah, that's Mars.
Yeah, so just offset. Yeah, so we're really digging out here, right? Gonna keep digging. Gonna put some of the brewskis in there. Get ready for the party, guys.
Yeah, you gotta go a little bit more north. Stick it in the ice, in
Yeah.
the dry ice. You'll be good.
Yeah, it'd be happening.
It'll be popping.
Yeah.
So next slide, please. So what's on tap for the next episode?
Okay, so the next episode is gonna be STS 41. I think it's B. We repair the Solar Maximum mission.
Ooh. Okay.
Yep, that's this guy. Another satellite repair.
Oh wow.
I like satellite repairs because you get some good pictures of spacecraft.
Yeah.
Yep. Yep. So I'm also going to deploy the long duration exposure facility.
Oh, nice. Okay.
And as an unfortunate teaser, that's not bad. This is a bad teaser. This guy here, Dick Scobie, he is going to die on Challenger. So
well, spoilers.
we have our first astronaut who'll die in the line of duty, I guess. As a fun, happy thing to conclude on.
Thank you.
This really successful mission, all these cool things about Mars, and then death.
Yeah. Thank you.
Actually, I think MGS is still in orbit of Mars.
Probably.
I mean, it's dead, but it's because I know because I think Mariner 9 should have come down by now, and that thing's been up there since it's 1974-ish.
Yeah, it does have large drag flaps on it, so but it's above the atmosphere.
Well,
so.
it could have also put itself in an orientation, so it's it's the most
It's
streamlined.
like edge on.
Yeah, it's like, like that.
yeah, it's doing like the like Egyptian walk.
Oh yeah. Fly like an Egyptian.
Burn up like an Egyptian.
Yeah.
Yeah. So that was Mars Global Surveyor. What did we learn?
We learned a lot about Mars.
Yeah.
We learned some geology. We got to count some dust.
Oh yeah. I learned so much researching this mission. Jeez.
These are really in-depth missions. It's not like you do in Kerbal Space Program. You just slap a few things on and go.
Yeah, it's
This one's kind of like that. You slap some science equipment on and go, but
yeah, this thing was basically rushed out the door.
yeah, built this flight.
Just duct tape it on.
Yeah, come on, guys. This is what they're doing at in the processing facility.
Yeah. They were MacGyvering it.
Yeah, it's a Swiss Army knife. That's what Jam did. It's a Swiss Army knife.
That would fit in there. Yeah,
That's about right.
MacGyver Swiss Army knife added another year to MGS.
Yep, it broke it. This is a fun mission.
This was great.
We went to
It's
Mars.
a decade-long mission.
Yeah, I got some good pictures of Mars too.
Yeah.
Oh yeah.
Oh yeah.
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 So do I end this now because you started it?
Yep, I started this. You end it.
Well, everyone, this has been End of Mission.